Gardens and to explain them and show you some really, really neat mathematics. Please welcome Dr. Marty Ross.
Thanks, Simon. Thanks. Yeah, that was interesting with the Herald Sun. I don't think they'll have disappeared. Do we have... Are we up? We're up. We're not up. Are we up? We're up. Okay. Yes. Yeah, well, I'm sure we'll hear more about the Herald Sun. And actually, I think once they hear that the Mathematical Association has been hanging out at the Caulfield Racecourse for the last couple of days, they'll pursue the story with a little more vigor. So this is the Mathematical Gardens of Babylon, and of course what I'm encouraging you to do here is all go home and spend the rest of your lives writing in cuneiform script. That's what these talks are about, practical tools to use in your everyday life. So you can gamble in cuneiform if you like. This is the, I had reason to count, and this is now actually the 25th lecture of mine in this series, plus another 22 from Burkhard, 3 in front. And I think, to pat myself on the back, that's a hell of a lot of stuff to pretend to know about. This one's quite remarkable, the things which happen with this one. Who's been to the Babylonian exhibit, the Mesopotamian exhibit in the museum? Right, okay, not many. Okay, I think it's terrific. I thought it was really a great exhibit. I went to check out to see what they had in the way of mathematics, but I really enjoyed it. Definitely worth it, and not nearly as expensive as Tutankhamun. And this is the third in the kind of the history series of these talks, tying in with the exhibits. There's so I have to explain some of those things. Who's the kind of nice, fuddy-duddy old man on the left? And what's the pretty girl doing on the right? And the very first one was Rocky V and other Roman contributions to mathematics to tie in with the Pompeii exhibit. And it turned out the other Roman contributions amounted to nothing. It was an hour of making fun of the Romans. And then to fit in with Tutankhamun, we had the pyramids, the Sphinx, and other riddles. And this was a little different, but not that different. So Otto Neugebauer is the name of the nice fellow. He's, and this is a quote from his famous book, The Exact Sciences of Antiquity. He said, Egypt provides us with the exceptional case of a highly sophisticated civilization which flourished for many centuries without making a single contribution to the development of the exact sciences. Right, so this is about 1,500 years, and mathematically they did pretty much nothing. And this, another quote, and this actually turns out to, there's an interesting debate going on. Ancient science was the product of very few men, and these few happened not to be Egyptians. Okay, and then that's an interesting question. We'll come back to that question about the idea of mathematics being the product of very few men. All right, and now we've got Babylon. And again, Otto Neugebauer he's the towering figure in looking at the mathematics of well, what we'll say is Babylon. I'll try and be a little more careful with the words as we go. He was, along with a guy called Francois, I forgot his name. Francois Thoreau-Dagen. He was the great translator of tons and tons of mathematics in the 30s and 40s. And he wrote a book, basically mathematical cuneiform texts in German, and then there was an English version with lots of plates. It's an absolutely, it's quite a beautiful book. Come up and look afterwards if you wish. And they sort of thought of him as being the great guy, but it's just astonishing how much there is to analyze. When you go to look at the Egyptian mathematics, I mean, they didn't have that much mathematics, but we also don't have much record of it. They wrote on papyrus, and it decayed, and we've got very little left, and basically any grocery receipt which happens to have lasted is considered a treasure. Whereas with the Babylonian material, there's just literally tens of thousands of these cuneiform tablets. A recent book, probably the one I found the most helpful in general, was one called Mathematics in Ancient Iraq by Eleanor Robson, who I think is probably one of the great scholars of this area, and really annoyed me for reasons I'll explain. And there is online, there's the Cuneiform Digital Library Initiative, which is just a magnificent thing at cdli.ucla.edu. And that is trying to put up on the internet as many of the photographs and information about the various cuneiform tablets from the various museums, so that the actual researchers don't have to go, travel 3,000 miles to Iraq and then take a photograph and say, oh damn, I forgot to photograph that one. Then the information's all there for people to puzzle over. It's quite astonishing how much is there, and also astonishing how much isn't there. There's still tons to do. The sad thing is, I mean, there's a lot of it got lost in the Iraq War because the Americans were too busy cheering rather than protecting the museums. So a lot of the cuneiform tablets have disappeared, and probably for sale on eBay if you look hard enough. Now, this description of what's going on is meant to be very, very broad brush. Okay, and if there's Mesopotamian scholars here, please forgive me. So what we've got is this sort of Mesopotamian region is the region for the name for the region between the Tiger and the Euphrates River, and it was occupied by various people at various times. And ballpark Sumerians, roughly from about 4,000 to 2,300 BC. So we're talking about 6,000 to 4,000 years ago. And then the Akkadians came along. Oh, sorry, and that's sort of down in the south. There's a city there, Uruk, where a lot of the tablets came from, but a lot of other cities as well. And then the Akkadians had an Akkadian empire, and there was based on the ancient city of Akkad, and we don't know where that is. Okay, so we know a lot, but we don't know. And then there was the Babylonian civilization, ballpark, again, with a couple of hundred years of general chaos in between. And then the Babylonians, well, the Assyrians came in for a while, and as these empires, there's no kind of clear dividing line. And this is mixing races and times and geography and all sorts of things. But we sort of use Babylonian mathematics to refer to the mathematics of all these groups together. There was a city of Babylon that was the center of Babylonian society. Now, what did they do? The Mesopotamians, well, this is not the Mesopotamians. This is probably the very earliest, well, do you call it mathematics? What counts as mathematics? It's a bone with notches in it, a tally stick. And this is from about 35,000 BC. This one's the Bomba bone from Swaziland. And that's how long humans have been counting things or recording things in numbers. But things really take off when you get some kind of civilization. So we started getting tokens, and that was about 7,000 BC. So rather than notching things in sticks or stuff, you would give tokens to record transactions or to, kind of your receipt or whatever. And numerals, actually sort of symbols for numbers, that sort of came in about 3,500 BC, and then sort of writing in about 3,000 BC. And the tokens, the numerals, and the writings were all in Mesopotamia. The tokens were sort of further north, and then the writing was down south. And why in Mesopotamia? Well, I don't know, who's read Guns, Germs, and Steel? It's a wonderful book, just really wonderful. It's a general audience book. It's not but it's not hard reading, but it's just a wonderful book about the ways why civilizations grew or why they died. And it's just the conditions were right there. They had the animals that could be domesticated and the grains that could be harvested and grown. And eventually the cities got huge. So Uruk at 3000 BC was about 50,000 people. So we're not talking about little villages of guys fumbling with their math. We're talking about something where you've you've got to do something more than just say, hey, we've got to feed a lot of people here. We've got like 5,000 people over there and they're hungry. How much barley do we need or whatever? So as soon as you kind of develop this civilization, as you start getting a trade, you have to measure fields for agriculture, then you have to predict the seasons, then you get the mathematics going along with it. So Mesopotamia had the right agricultural and environmental background in order to start civilization, and then the maths kind of takes over. Well, it doesn't take over, but if I had my way, it takes over. Now, the very first numerals, so Sumerian numerals, now this is, again, there's sort of like lots of competing things, but this is sort of one version of it we see in some of the tablets. So they had a symbol. These are all made in clay with a stylus, and they're all easy to make with one point to the other. So they had symbols for 1, 10, 60, 600, 3,600, and 36,000. So there's kind of some multiplying by 10 there, but also very notably multiplying by 6. Why? Why 6? Why 60?
Because it has a lot of factors.
It has a lot of factors, exactly. So there's an early one, but these are all what they call metrological units. You've got to be careful about it. It's not clear. It's not like they gave us a user manual and frequently asked questions as to Mesopotamian tablets. There's very little information to go on, and you're trying to figure out what this stuff means. But it seems clear that these were units. It wasn't the number 10 so much as it was 10 cubits or 10 gur or 10 this or 10 that. And often the same symbol would be used for different quantities in different contexts. And it's quite different from thinking of things as numbers. And I'll sort of give an example. Here's a carton of eggs. Okay? So if you're told to go down to the shop and get a carton of eggs, all right, it doesn't mean a dozen eggs, but it has the effect of a dozen eggs. All right? So you might have a word like carton, which initially just means this kind of display of eggs, but eventually could turn into a number 12. And that's sort of the same thing with units. You've got things like one band. These are just very old Sumerian units. One bariga equals 6 band. So that ends up being 60 sila. These are units of grain, I think. 1 gur equals 8 bariga. Why 8? Well, eventually that changed. It was 5 for a while, and then it was 4. These things weren't constant. They were just trying to figure them out. But the numerals fit in with their units of measure. Now, of course, we've got, what are our units of measure these days? Well, we've got liters and milliliters, and we've got centimeters and meters and kilometers. So which is better? Millimeters and centimeters, or feet and inches? All right, and here's where I'm the crazy American and his conspiracy theories. I think feet and inches is much, much better. Yes. I need to add some surprises. Maybe if I'd gone for the metric system. Actually, there's sort of things here. I mean, I'll make some fun of the national curriculum at times. And one of the things is just the national curriculum and its focus on decimals. But that's kind of a separate issue. That's a different issue from the kind of 60 or 10. But it's just anything, the fact that 12 and 36 inches in a yard, it's just, you can divide it easily, which is exactly why we have 60 minutes in an hour, 60 seconds in a minute, 24 hours in a day, so you can divide the day up into nice little portions. No one's, have they? Has anybody suggested doing metric time? Millie Marty? The French? Really? But do they really use it, or they just pretend?
They really used it for a short time.
Oh, for a short time before they realized it was crazy. Well, eventually. Yeah. All right, so they introduced it at the same time as they introduced metric for everything.
Yeah.
Right. Okay.
It lasted for 5 years.
Right, but it's kind of the point, right? Well, there's two things here. One is, I mean, why 10? Well, if you're gonna, if you multiply by 10, that's easy, right? So, 30 centimeters times 10 becomes 3 meters, and so on. So that works very well if you're doing arithmetic. If you're simply dividing something into smaller portions, then the more factors the better. Right, so it does depend upon the use. Whoever said that's correct, but in general, we don't do a lot of arithmetic with things. We're just sort of dividing things into portions, and feet and inches tends to work better. All right, that's my own personal crusade. Now, here's a Sumerian schoolwork problem. Again, this is from about 2,500 BC. And roughly, this is what's described. We've got 1 granary, 7 selas, which is a unit of grain, amount of grain, 3 selas left. And then the number on the right is 4 times 36,000 plus 5 times 3,600 plus 5 times 600 plus 2 times 60 plus 5 times 10 plus 1. And then there's a word for men or people or workmen or something there. And it's 164,571. And what this problem is doing is the granary amounts to, well, if it amounts to 100, one is kind of figuring out what the units are from the problem, the other is figuring out the problem for the units together. But basically, how many men can you feed if they each get 7 selas of grain each? The answer is you can feed 164,000 more or less men with 3 left over. Okay, so this is a kind of problem, and this sort of question is whether this is actually someone actually trying to feed men. Are they actually doing bookkeeping, or is this schoolwork? And the answer is it seems to be schoolwork, because there's another tablet which is almost identical, except they get the answer wrong. It's quite remarkable, the things that they find. And it's not that long ago that it was noticed that there were 2 tablets talking about the same problem. I think it was Marvin Powell, I think is his name, in the 70s, I think. And it's just fascinating to get these two tablets on the same problem and then trying to work on that. There's actually, we've got some school, do we have teachers here? Yep. There's a funny thing in textbooks they get a lot. I tutor here and there at time, and one of the kind of problems that textbooks seem to love these days is you might be kind of teaching algebra, and Johnny gets the answer a squared plus b squared rather than a squared plus b squared plus 2ab, whatever. How did he get the wrong answer? And when I'm tutoring this, I just feel like saying, well, why don't you just write down that Johnny was drunk at the time, something like that. I mean, there's a billion ways to get the wrong answer, and it's kind of something imprecise in the nature of that question. But this is exactly the situation that these detectives, these archaeological detectives or anthropological detectives are looking at. How did this guy get the wrong answer? What clues does that give us about the way they actually did the calculation? Because the calculations aren't here, right? It's really just the number and the answer. And so that, it's still not clear, but you get more or less plausible answers about the way they actually did the calculation. And 7 is a rather nasty number, of course. Dividing by 7 causes problems. Okay, now, the huge step, the first huge step, was the Akkadian numerals. Now again, Akkadian is referring more to the time than something specific about the Akkadian Empire. But we're talking around 2000 to 2500 BC. And they just replaced everything with the symbols for 1 and 10. So the vertical guy is 1, and what looks like an angelfish is 10. And this is the thing, and if you sort of look at that bit highlighted there, what you've got is that's a 10 and a 4, which is 14, and you've got 54. And what they've done is exactly what we do. So the same way we say 737, that means 7 hundreds, 3 tens, and just 7 ones, so that the 7 does double duty. Depending where it is, it can either mean 7 or 7 hundreds. Exactly the same thing is done by the Akkadians. But, and this is what's considered remarkable, is it's base 60. So it's 14 times 60 plus 54, which, if I did my arithmetic correctly, and it was 4 in the morning, so who knows, is 894. So they use what we call positional notation. They were the first to use it. And it's just remarkably powerful to simply get away with those 2 symbols, sort of. There's a problem there, but pretty much get away with those 2 symbols and just use the placement of the symbols to mean higher quantities. And it's really the heart of it. And in previous talks, I made fun of the museum because they had education kits. They had education kits on Egypt, like for history and geography, which all made sense, and for English. I'm not sure how you have an education kit for English on Egypt, but they had no mathematics. But they do, for Mesopotamia, they do have a maths education kit designed, they say, for year 7 students, and you go through some very good exercises on Babylonian numerals. It's really, it's very well done. Now, who came up with this? How did they come up with this? Where did they make the change from going like this kind of Roman numeral style, where you just kind of pile things on more and more? I should say also they did the kind of subtraction thing the same way Roman numerals do, that IV means 5 minus 1, VI means 5 plus 1, things like that. But nonetheless, it's hugely cumbersome. So who made the change? Or how did they make the change? Was it inevitable? And this is sort of the heart of the Babylonian debate. As I say, in the 30s and 40s, they were just overwhelmed with how much mathematics the Babylonians knew, and the Akkadians, the Sumerians altogether. And they were just sort of writing things down and saying, my God, did you realize they knew this, they knew that? Now, there's much more focus on how did they know it. And was it kind of inevitable in the way the society grew up? So semi-inevitable, that if you just start it the right way, it kind of ticks over in the right way. Or was it some Einstein that kind of just said, I've got a great idea? And you know, there's no answer to this, but one thing is, there's the weights at the time was 1 mina was 60 shekels, and 1 talent was 60 mina. So that the units later, at least for weight, were multiples of 60. And so it's very simple to somehow to get to this. And at times, I think 10 shekels was used to mean 1/6. 1/6 of a mina, but it was used in general to mean 1/6. Even when not talking about weight. So there's an idea that, well, maybe the units kind of made this notation inevitable. And I say these are very involved and very difficult questions, also very testy questions. It's amazing how many people in this field dislike how many other people in this field. There's a lot of big egos. Just some remarkable things, and just looking at the reviews of this and that, and what people say about this, and you know, the Right Honorable Mr. Johnson doesn't actually know what he's talking about. And it's a very, very grumpy debate about this. And I'm certainly not going to enter into it. I can't enter into it. There seems to be the suggestion that there was some Einstein, that this wasn't inevitable, that it really someone had to have that brainstorm to use the units over and over again the way we do. That it really wasn't. But it's not an obvious thing, right? They're definitely, the units kind of suggest maybe positional notation, but to actually use positional notation is quite, seems to be conceptually, and the evidence seems to suggest that. But again, I mean, this is a debate for experts. Now, there are troubles with this notation. This isn't real trouble. So the first one just means 4. And the second one, because of the gap, well, that means 2 times 16 plus 2, which is 122. So as long as you kind of put a gap between where you want the kind of 1, the 60's place to start and the 1's place to start, it's okay. Of course, when you're writing down your homework, you tend to do it very quickly. You don't always leave good gaps. And so there's lots of mistranslations and things like that. There's lots of cases where it's just not clear what number they're trying to come up with. And then the question is, well, let's suppose the number was 122. What would that make the problem to be? And so there's a lot of kind of reverse detective work to try and figure out what the numbers were. There was ambiguity. There were also, they had other ways of writing things. Sometimes they used multiplication, so that a 2 next to a 10 might mean 20 rather than 12. So there's all sorts of things they did. A much greater problem is given by this number. So what should that be? So 1 times 68 plus 12, 72. But the problem is, I'm sure some of you are aware of this, when we do positional notation, we've got something which really helps us, which is what? 0. Okay? So if we want to distinguish 43 or 403 or 430, we put a 0 there. Okay? And so the same way, we've got a 1 and we've got a 12, but it could mean 1 times the next place up, 3,600 plus 12. Or it could be 1 times 3,600 plus 12 times 60. So how do you know which one it is? Well, in practice, what they did was, it was context. So, if I tell you to go out and buy me 112 beers for a party, obviously I mean 4,320. Right? Big party. Is anybody from the Herald Sun here? It's okay. So the context would usually indicate it. Eventually, long after, so I'm sort of talking about the Babylonians. The highlight is kind of 1800 to 1600. Eventually, they did introduce a 0. They introduced a position thing over there to indicate a space. So that with that symbol in there, this kind of double slanted little ones, guys, and there are various symbols they used, that would indicate the middle number there, 3,612. So 1, 3,600, no 60s, and then 12 at the end. And that was much later. That was around 500 BC that we seem to see these things. Again, it could, there's evidence slim at times in this whole period of which we know nothing, so it could have been earlier, but it certainly wasn't at the height. And also, they never used it in the final position, so they would never write 430, or the Babylonian equivalent for 430. So that context, they never used it as the final digit, so to speak. It wasn't, and also it wasn't a 0 in the real sense of 0 as a number. All right, so they didn't do calculations like 5 plus 0 equals 5 or 5 minus 5 equals 0. It was simply a placeholder saying no 60s here. Okay? But it's absolutely phenomenal what they did. It took a long, long time for this to be rediscovered. It was the Indian mathematicians, so a good 2,000 years later, if not more, to get positional notation. I find that we have. Okay, now this is quite a maths-heavy talk. It's math talk. I should say there's some maths at 10:30 in the morning. I was initially skeptical about the time, but for a talk on the dawn of civilization, it seems appropriate. So. Anyway, we do like to include maths clips, and there's a whole book written on maths in the movies, written by a couple of Melbourne ne'er-do-wells, and not a single piece of Babylonian mathematics in it. There is one clip. Unfortunately, this clip is rather violent, so we've had to adjust it slightly. Herald Sun people, okay, all right.
Well, that's one of the 10 Commandments. I'm Father Brian.
No, Father Brian, I take it very seriously when people are tortured and killed.
Well, then I'll skip the small talk. Do you know what this writing is, what it means? It is cuneiform.
Cuneiform?
The world's first written language, created over 5,000 years ago by the Sumerians, later adapted by the Akkadians and the Babylonians. It's what our alphabet evolved from. This looks like the Babylonian version.
What does it say?
It's not math, so we don't care.
This one I can read. It's very simple. It means 4. That means 16. 4 down, 16 to go.
Oh, that was worth it, wasn't it? All right, so there are Babylonian numerals written in nice fresh blood. As you can see, the 4 doesn't really look like it's a 16 there, but I'll take their word for it. But anyway, if there's any mass murderers in the audience, leaving clues in blood written Babylonian cuneiform is really stylish, so just take that tip away with you. Okay, now Babylonian arithmetic. We've got the numerals, but how did they do arithmetic? Well, how do you do multiplication? All right. Well, you use a multiplication table. And they had tons and tons of multiplication tables, unlike the national curriculum. All right, so yes, we're more in the Sumerian era. All right, so this table, this multiplication table, this turns out to be multiplying by 160,000. You never know when you're going to need to multiply by 160,000, so it's good to have that table. Keep one with you at all times. Okay, they had lots and lots of multiplication tables. And, well, derision, to quote Lewis Carroll. Now, all right, now I'll give you a question. 194 divided by 5, what's that? 38.8. How'd you work it out? Doubled and divided by 10. Okay? So times 2 divided by 10. You didn't think there were going to be quizzes. Okay? But that's the thing. Divided by 5 is you times 2, and then you just move the decimal place. Actually, teachers get grumpy if you say move the decimal place. It's best to move the number, but we'll move the decimal place. Just annoy them. So it's 38.8, as long as, again, it was 4 in the morning. Okay? So one way of dividing, at least if you're dividing by the correct number, you know, a useful number is to multiply and then divide by 10. And what would the Babylonians do, or the Akkadians, or the Sumerians? 194 would be times 12 divided by 60. Dividing by 60 is what moves their decimal point. Doesn't make sense. Sexagesimal point for those who like the jargon. Okay, so they can do exactly the same thing. What about 194 divided by 3? Well, there's no real trick for us, right? I mean, you just got to do it. You can do the decimals if you like, but it doesn't work the same way. But for the Babylonians, it'd be times 20 divided by 60. So this is where even the base 60 works, in some sense, much nicer. I mean, there's a trade-off, right? 60 is a lot of things to have in one little spot. But it makes this kind of division by multiplication work much better. And as it turns out, 1 over 81 is 160,000 divided by 60 times 60 times 60 times 60. So if you want to divide by 81, the way to do it is to multiply by 160,000 and then move the decimal point 4 places. So in fact, why did they have a multiplication table for 160,000? Was really so they could divide by 81. So that's, and you know, which is, you know, again, it's not something you do every day, but it's something to have handy. And of course, they needed that in their own notation. So 44 in the 3,600s place, 26 60s and 40, and they had tables of reciprocals, 1 over the thing, and there, you know, they had tricks like this to do it, and they had tons and tons of tables of reciprocals. If you go to the exhibit in the museum, the very first exhibit that you see just as you walk in is a table of reciprocals. It's a beautiful table of these reciprocals. Okay? And you know, if you sort of write out the table, it sort of looks like this, and you do the same for us. 1/2 is 0.5. 1/3 is annoying because it's 0.333 ... and so on. Whereas for the Babylonians, it's just 20 over 60. You know, so it's kind of 20 in that spot. Of course, they still have troubles, right? They don't have 1 over 7 is annoying for us both equally. And that first problem we looked at, the granary problem, dividing by 7, it seems clear that 7 was chosen exactly because it's an annoying number to divide by. And the early tables, the early Babylonian tables, simply left out those numbers. Okay, so basically they had 1 over a number if the number was built up from 2s and 3s and 5s. But 7s and 11s and so on, they just left out. Later, they did have approximations to these numbers, and you can do it. The base 60, the Babylonian expansion of 1 over 7 looks like that, and then it repeats. Yeah. Okay. So they did that. They also they had lots of work. It's not like they had reciprocals for everything. So for example, 1 over say 125. They didn't tend to have 125 in their table. So they had methods of calculating even numbers built up like that from smaller numbers. And as one of the writers put it, he went through the technique they used in nauseous detail. It's remarkably boring paper. But he goes through it and describes exactly the way they calculated various reciprocals. Right. What about their geometry? Well, this seems to be the very first maths problem per se that we know. And there's not much on it. This is a cuneiform tablet. There's, on one side is one problem, and one side is the other problem. And you've got to kind of make up the problem from the numbers there. So what we've got is units of length, 980, 1,420, 520, 1,280. This is about 3,000 BC. And then there's kind of vertical and horizontal lines. So these are Sumerian numerals you've got there. And if you put it together, something like that. Now, one thing you can do is you can say, well, sort of like a rectangle. Sort of. Well, not really, sort of, but you take the 980 and 1420, so that's the average of those two sides. 1280, 520, that's the average of those two sides. Multiply it, and hopefully you get the area. Well, you don't really get the area, and in the Roman talk, I made fun of them for using this as a formula for area. It's actually well known for these kind of, it's kind of called an agrarian method of calculating areas, clearly only approximate, and it doesn't work very well. But this seems to be what the problem was about. Okay, so not great geometry, but it did get better. That's why we talk about it. Now this is the Babylonian superstar, one of a number of Babylonian superstars. So this is from the Yale Babylonian collection. I think this is from Bill Castleman. There's some beautiful photographs. If you go to that website, I said CDLI, you can find just gorgeous things on these things. And this is Bill Castleman. So what he's done is he's highlighted there the numbers which are displayed. Sometimes it's hard to see the numbers. What you've got there is 30, 1, 24, 20, 51, 10, 42, 25, 35. So what's this about?
That's all I remember.
That's That's right, that's a lot of numbers, and you should all go out and buy lottery tickets because we like gambling. Okay. So, one thing is, if you do 30 times 124, 51, 10, you get 42, 25, 35, which seems impossible because the purple number is bigger than the blue number, but they just move the decimal points around. So multiply by 30 and then move the decimal point. Okay? So what some saying is that if you multiply that purple number along the diagonal by 30, you get that number. What's the 124, 51? Well, 124 is 1 plus 24 over 60, which is about 1.4. What this is doing, the square, that's 1, 1. And Pythagoras' theorem, Pythagoras was about 1,000 years later, so I don't think the Babylonians called it Pythagoras' theorem. That's the square root of 2. 1 squared plus 1 squared equals 2. So you're looking for something whose product is 2. And so this number, the 124, 51, 10, is their approximation. So think of it as 1.24, 51, 10. So it's 1 and 24 60ths and 51, 3,600, 10, whatever the next guy is. So it's just remarkable. So it's clear, I mean, it clarifies a bunch of things and then also raises a lot of things. Is they knew Pythagoras' theorem. They knew it at least they knew it in this case. This is kind of the simplest case where the a squared and the a and the b are the same, except it leads to a square root answer, which is annoying. But how did they get that approximation, and how good an approximation it is? And this is what's stunning. Is you're looking for a number. If you're trying to get this diagonal, you're looking for a number, the hypotenuse, such that its product is equal to 2. How could you find such a number? I mean, well, how could you guess such a number? How could you estimate such a number? The simplest way you might do it is simply by bisection, right? And you know 1 is too small. 1 times 1 is 1, 2 times 2 is 4, so you need something in between 1 and 2. So you just go in the middle. You go to 1.5. Now you multiply 1.5 times 1.5, that's too big. So you say, oh, you go in the middle of 1 and 1.5. That's 1.25. And you 1.25 times 1.25, and that's too small. So you go 1.375. That's too small, so you go in the middle and you keep going. So each time you have the distance, and you'll get there, right? And each time you can check whether the guy you've just done is too big or too small, and you divide one way or the other. So this is the method of bisection, and this is very well-known method, very kind of safe, reliable, clear, understandable method, and it's not what the Babylonians did. What they did was quite remarkable. It seems what they did. Again, all we've got is the tablet. But this is what they did. Okay, so again, let's start with 1 and 2. And let's just say we guess 1.5. And 1.5, again, is too big. Now what you do is you compare that to 2 divided by 1.5. And their product is equal to 2, of course. Well, if 1.5 is too big, the other number multiplied to give 2, that must be too small. So now you've got 2 guesses. You've got 1.5, which is too big, and 2 divided by 1.5, which is too small. So what you do is you average them. And if you average them, you end up, in this case, if you start with 1.5 as your guess, you end up with 17 over 12. Which in decimals is about 1.46, I think. It's remarkably close already. But then you do it again. So you say 17 over 12 is too big. 2 divided by that is too small. I can't remember whether it's too big. Yes, too big, I think. Divided by that is too small. Take the average. And if you do that, what you end up with in Babylonian notation is 124, 51, 10. So what they've done is, it seems that this is what they've done in one form or another. This is known as taking the harmonic mean of 2 numbers, and it kind of fits in with the fact that they liked to play with reciprocals and kind of knew about dividing by things. But this seems to be, it's not a total explanation of how they did it, but it seems to be the heart of what they did in that problem, and it's quite remarkable. For those of you who know about Newton's method gives you this same answer. Newton's method turns out to give you the same harmonic mean thing in this case, for trying to find roots. Now, they didn't know Newton's method, right? They didn't do that, but this technique is, again, it's remarkably accurate. All right. Okay, here's another superstar, Plimpton 322. This is probably, in some sense, the superstar. So the Greta Garbo of Babylonian mathematics, and she's sort of the perfect symbol for it because she's beautiful and no one could make heads or tails of her. Just kind of inscrutable. And Plimpton 322 is just an incredible tablet. And again, it's a list of numbers in columns. And columns, I've labeled them D, A, and C, and those are the numbers. And bits are missing, the left is missing, it looks like there may have been whole other columns there. We don't know where it's from. It was kind of bought in the market in, I think, late 19th century, early 20th century, something like that. It's just, some dealer said, yep, I got this, yeah. Here it is. And the bit was broken off. It was glued together, and apparently the glue broke. So somewhere it survived, but we don't have it, is the rest of the tablet, or at least more of the tablet. And this is the kind of thing which confronts these guys when they've got tens of thousands of tablets. Is here's a tablet with a whole bunch of numbers, and you think, oh well, what's that? Well, I don't know. Maybe could be granary stores, or it could be soccer scores, or whatever, right? I mean, who knows what it is? And so it's the kind of detective thing out to figure this out. And Neugebauer and a guy called Sachs in the 30s and 40s, they figured out Plimpton 322, at least in heart. And it's Pythagoras again. A squared plus B squared equals C squared. So if you think of the middle column there is the A, so that's 119, and 159 is 119, and the C, the first entry there is 169. Okay? Then what's the first column? Well, the first column turns out to be C over B squared. And so, for instance, the first column is corresponding to the Pythagorean triangle, 119 squared plus 120 squared equals 169 squared. So you play around with these in school all the time. 3 squared plus 4 squared equals 5 squared, whole number solutions. And all of these are corresponding to whole number solutions. Of course, that, so it's, and you look at them all, and there's a couple of errors, I think there are things which are indecipherable, but they're all Pythagorean triples. They're all correspond, they're not triples themselves, but the A and the C are from an equation in whole numbers, a squared plus b squared equals c squared. And of course that just starts the mystery. Is how did they get these numbers? Why did they list those ones? What's in the pattern in the table? This debate is still going on. And one of the papers, you know, the great thing about these lectures, for me, is I get to learn all sorts of things, which I kind of knew about, but didn't really know about, and still don't really know about, but I learned a lot more about. And you sort of just looking at what these very intelligent people did. And one of the papers I really loved reading was Sherlock Holmes in Babylon. And this is available online, so if you just Google Sherlock Holmes in Babylon, it'll come up. And this is a recent paper, a relatively recent paper, about 30 years old. And it goes through trying to figure out, first of all, how might you guess, how might you figure out, just given those numbers, how might you play around and figure out that they're actually corresponding to Pythagoras' theorem? And then what did these numbers mean? How did they come about it? And there's various theories about it, and Creighton Buck sort of suggests one theory. And it's that, I mean, one of the things about the D table, if you think of the one, the one at the start, you think it as 1 point, ... those numbers are decreasing. And it basically corresponds to like a trig table of decreasing angles. Now, no one actually thinks it's, well, they didn't have trig in any sense. But whether this was, if that's the point of it, is not clear. Anyway, as I say, it was a great paper. It was really very enjoyable to read. And, you know, it gets kind of detailed at the end. It's not difficult, but there's nothing kind of really technically difficult about it. But it, you know, it takes some work to read through it, but it's a very nicely written paper. And it also is probably complete nonsense. Here's another one. This is Eleanor Robson. Neither Sherlock Holmes nor Babylon, a reassessment of Plimpton 322, where she takes great issue with this paper, another paper. And it brings to light the kind of nature of this kind of debate. Is Creighton Buck, it's kind of the mathematicians versus the sociologists, anthropologists. And the mathematicians are looking at this and they're saying, how can we make this mathematics, what's the heart, the mathematical heart behind these numbers? And how can we make mathematical sense of this? And Eleanor Robson, not just her, I mean a whole school, is saying, well, you can't divorce these numbers from the reality, from the cultural and social reality in which the numbers came. And the way to understand these numbers is much more, how could they have arisen by the society which demanded them, rather than individual acts of brilliance. And there's no one clear answer to this. I suspect, unfortunately, that Eleanor Robson is probably right. Somehow she argues her case, whereas Buck is looking, the mathematicians are looking for beautiful mathematics underlying these numbers. Robson is looking for the cultural reality, which is much less of Einstein's and much more the units of measurements and the way they kept tables. And she's sort of arguing that there was no Einstein behind this, that it was kind of the nature of the tables they took. It's a very complicated debate. And as I say, it's a very grumpy debate. Neither Sherlock Holmes nor Babylon, nor Babylon is a cheap shot because the table was not actually found in Babylon. It's clear it came from southern Mesopotamia. So she's getting annoyed that we keep calling it Babylonian mathematics, even though it's got nothing to do with Babylon. Anyway, it's a remarkable tablet, and there's still, you know, as I say, there's tens of thousands of these tablets, and you know, there's so much work on just a few of these. Not all the tablets are that interesting, but a lot of them are. Okay, a quick bit of comic relief. This is from the Yale collection, and this here we've got a circular tablet. And there's a circle in the middle, and it's got the numbers 3, 9, and 45. And you've got to figure out what this means. That's all there are. There's only numbers. But it's got something to do with circles. And a reasonable guess is that the circumference equals 3, and the area is equal to 45 over 60. If the area was 45, it wouldn't work. So just, again, change the decimal place. Okay, and if you do that, so area is pi r squared, circumference is 2 pi r. We don't actually teach a formula relating area to circumference directly, but you can get it from those formulas. You just do some jiggling, and if you do that, then pi pops out, and pi pops out to be about 3. Which, given all the other impressive stuff they did, is very impressively unimpressive. And it seems that this is pretty standardly their number for pi. That there seem to be a couple of tablets where they use 3 and an 8, same as the Egyptians, but they, given the remarkable geometry they did and so many remarkable numbers, this is kind of amazingly poor in the sense that they would use pi equals 3 all the time. They didn't seem to do circles very well. Some of their other formulas are wrong. Volumes of chunks of pyramids and cones they weren't very good at. But they did. Now, last one. So, this is the Hidden Beauty. And of course, well, I'm talking about the picture on the left. The beauty on the right is not hidden. This is another very famous tablet. And this tablet, you translate it, it says, added to the area the excess of length over width. So this is again a school problem. And then the answer is given as 3, 3. That's 3 60s and 3. 183. Added length and width. And the answer is given as 27. And then the problem is to find the length and the width. So the length times the width, that's the area, plus length minus width is 183. And the length plus the width is equal to 27. Find the length and the width. Okay, you've got 2 minutes. Okay, all right. So I made a vow that no quadratic equations before noon. And that's exactly what you need. So you do it.
X equals negative b or c plus or minus the square root.
And so on. Okay, all right. Okay, so you older guys, you remember that somehow. It's there as a mantra there, and you might remember it with the B or the C or whatever. Okay, so it's quadratic formula one way or the other. Now they didn't have a quadratic formula, but they had methods which amounted to the quadratic formula, completing the square, and they could pretty much solve any quadratic equation, and tons more. Tons more. They had. They were very good at these algebraic equations. But there's something actually quite remarkable about this, and there's just one last point I want to make on this. So this is finally, you're probably wondering all the time, how did I get a Twin Peaks person into a talk about Babylonian mathematics? Here it is.
I've been doing some research. In real life, there is no algebra.
That's it. In real life, there is no algebra. And that's true, of course. And in real life, there is no numbers, right? Remember, in the very early days, the Sumerians, we're talking about, a carton of eggs is not the same as dozen eggs is not the same as 12. But algebra, even less so. Now, their algebra problems, and this is effectively an algebra problem, well, they're talking about area and length and width, so that's still very physical. But what's absolutely remarkable about this question is they've added area and length. Those are completely different things. The notion of adding an area to a length like that is really treating those numbers, those quantities, in a very abstract manner. And it suggests an inventiveness and a playfulness in the mathematics. In some sense, I think this is the most remarkable part of Babylonian mathematics, is they were willing to, it indicates they weren't just calculating areas of fields or this or that, they were actually dealing with the numbers. They were trying to understand the way the numbers worked, and did remarkably well for it. I mean, they did just stunning things. It really is a mathematical garden. As I say, the exhibit is terrific. The very first thing in the exhibit at the museum, table of reciprocals, and it's just, it's indicative of just the beautiful mathematics is there. And thanks. Thank you very much.
Just before we go, does anybody have any questions? I've got a microphone because that way we can record the question.
Or you can yell.
Question?
Yep.
Marty, does Robson attempt to explain why that column D in Plimpton was in order of angle?
She does, and she seems to think, what she emphasizes is, again, somehow, it's clear that they wanted the column D to be descending, that's clearly not coincidence. The question is, how did they get it? And she, and also why, she's arguing that it's, first I'll say, the mathematicians argue there's very nice formulas to come up with Pythagorean triples. So you pick your two favorite numbers, and I'll come up with a Pythagorean triple for you. And you probably know these methods. Robson is saying they didn't do that. That it was much more a natural outgrowth of their playing with reciprocals, and they're using reciprocals as to how they came up with the numbers. Again, what exactly, why they would use the numbers, in some sense, well, right-angled triangles are very useful. Why are they useful? Not obvious, I guess. Well, one thing is, how do you make a right angle? You know, suppose you want a nice square field. How do you make a big right angle? Well, one thing is let's say get a piece of rope 12 thingies long and make it into a triangle of sides 3, 4, and 5, and then you'll have your right angle. So having right angles, and having angles and being able to make angles of different size, right angle triangles, so having this kind of table meant they had a whole bunch of measurements. So it's kind of natural that they would want these triangles of kind of varying, right angle triangles of varying angle there. The question is how they came up with it. As I say, Robson's arguing for this sort of emphasis on the reciprocal rather than kind of abstract, brilliant formulas that the mathematicians love. As I say, it's a very touchy debate.
You thank Marty Moss again.
Yeah.